Welcome to Calculus. Today, we are going to explore a fundamental topic known as the algebra of limits. If you have ever looked at a massive, intimidating mathematical expression and wondered how to even begin solving it, this is exactly the toolkit you need. It allows us to break huge problems into tiny, bite-sized pieces. Before we look at any equations, imagine you are at a grocery store buying a bag of apples and a loaf of bread. To figure out your total cost as you walk to the checkout, you do not need a special, complicated formula for apples and bread combined. You simply look at the price of the apples, look at the price of the bread, and add those two numbers together. In calculus, the concept of limits works in the exact same intuitive way. When faced with a massive expression, you find the limit of each small piece separately, and then just add, subtract, multiply, or divide those simple answers to get your final result. Now that we understand the intuition, let us look at the formal mathematical rules, starting with the sum rule. Conceptually, this just says that the limit of two functions added together is exactly equal to the sum of their individual limits. In this formula, c is the target value our input variable x is approaching. L and m are the final numerical values that our individual functions approach. So if the first function is heading towards 5 and the second function is heading towards 3, the combined function is heading towards 8. It is that simple. This holds true no matter how complex the individual functions are, as long as their individual limits exist. Building directly on the idea of addition, we have the difference rule. Just like addition, subtraction works perfectly with limits. This formula states that the limit of one function subtracted from another is simply the difference between their individual limits. If you know the destination of the first part, which we call L, and the destination of the second part, which we call M, you just subtract the second destination from the first. As the values of L and M change, the final result changes in direct proportion to their difference. If L increases, the final limit increases, and if M increases, the final limit decreases. Our next tool is the constant multiple rule. Think of this like buying 3 identical bags of apples. You just find the price of one bag and multiply it by 3, rather than scanning every single apple. Here, k represents any constant real number, like 2, -5, or 0.5. A constant is just a fixed number that does not change as the variable x changes. This formula tells us that if a function is multiplied by a constant number, you can just find the limit of the function first and then multiply that final answer by the constant. If the constant increases, the final limit scales up proportionally. Before we move on to more rules, let us see these first 3 rules in action with a concrete example. We are given a problem where we want to evaluate the limit of the polynomial function 3x squared plus 5x minus 4 as the input x approaches the number 2. Looking at the entire expression at once might seem like a lot of mental math, but our strategy is to use the sum and difference rules to split this single large limit into 3 smaller separate limits. We distribute the limit operation to each of these terms individually, which makes the problem much less intimidating. Continuing with our problem, we now have 3 separate smaller limits. The first term has a constant multiplier of 3 and the second term has a constant multiplier of 5. According to the constant multiple rule, we can pull these numbers outside of the limit operation to make the expressions even simpler. At this point, the limits are as simple as they can possibly be. Since these are continuous functions, we can find their limits by simply substituting the target value, 2, into the variable x. This step transitions us from calculus back into standard arithmetic. Now that we have successfully evaluated the limits and replaced them with their numerical destinations, the calculus portion of the problem is completely finished. All that remains is basic middle school arithmetic. Following the order of operations, we square the 2 to get 4 and multiply 5 by 2 to get 10. Multiplying 3 by 4 gives 12, adding 12 and 10 gives 22, and subtracting 4 leaves us with a final answer of 18. Physically, this means as your input gets closer to 2, the output height of the curve approaches 18. So we have used the sum rule successfully. This brings us to an important question. How do we know it is actually true? In mathematics, we cannot just state that a rule works. We must prove it beyond any doubt using the formal epsilon delta definition. Epsilon represents our allowed error or tolerance in the final output. Because we know the individual limits exist, we can control their errors independently. We choose to force the distance between each function and its limit to be strictly less than half of our total allowed error, which we write as epsilon over 2. We do this by restricting our input x using small distances, delta 1 and delta 2. To ensure both error conditions are met simultaneously, we choose a new delta that is the minimum or the smaller of delta 1 and delta 2. Think of it like a security clearance. If one door requires level 3 and another requires level 5, having level 5 guarantees you can open both doors. By choosing the stricter distance, we guarantee x is close enough to keep both functions within their allowed half errors. Now we look at the total error of our combined function. We want to find the distance between our combined function and our combined target, L plus M. By using basic algebra, we rearrange the terms inside the absolute value, grouping f of x with L and g of x with M. This algebraic rearrangement does not change the value at all, but it sets us up to use a powerful mathematical tool called the triangle inequality. This fundamental rule states that the absolute value of a sum is always less than or equal to the sum of the absolute values. By applying this rule, we split our combined error into two separate manageable pieces that we already know how to control. We substitute the bounds we established earlier. Each piece is less than epsilon over 2. Adding those halves together exactly equals our total allowed error, epsilon. We have successfully proven that the total distance is strictly less than epsilon, meaning the limit of the sum is indeed the sum of the limits. Now that we have proven the sum rule algebraically, let us look at what it means visually. In this diagram, you can see our target point C on the horizontal axis. Look at the lowest curve, g of x. As it approaches C, it reaches a height of m. The middle curve, f of x, reaches a height of L. Now look at the top curve, which represents the combined function. Its height at point C is exactly equal to the height of f of x stacked directly on top of the height of g of x. The limits behave exactly like physical building blocks. Moving forward with our toolkit, we arrive at the product rule. This rule states that the limit of two functions multiplied together is equal to the product of their individual limits. Unlike derivatives, which you will learn later and which have a very complicated product rule, limits are incredibly friendly when it comes to multiplication. You simply evaluate the limit of the first piece, evaluate the limit of the second piece, and multiply those two numbers together. If either L or M is 0, the entire combined limit will also be 0. If the limit of one function increases, the total product scales up accordingly. Finally, we have the quotient rule, which handles division. It says that the limit of one function divided by another is the quotient of their individual limits. However, there is one massive, critical condition for this rule. The limit of the denominator, m, cannot be equal to 0. In mathematics, dividing by 0 is undefined and breaks our standard rules of arithmetic. If m is 0, this specific rule fails and you must use more advanced algebraic tricks to find the limit. But as long as m is not 0, you can divide safely. As the denominator limit m increases, the overall fraction becomes smaller. Let us apply the quotient rule to a rational function, which is simply a function that is a fraction containing variables. We are asked to evaluate the limit of 2x plus 4 divided by x minus 1 as x approaches 3. Because dividing by 0 is strictly forbidden, our approach here must start with a safety check. We evaluate the limit of the denominator by itself as x approaches 3. The result is 2. Because 2 is not equal to 0, the quotient rule is perfectly safe to use. We have a green light to proceed with splitting the fraction. Now that we know it is safe, we apply the quotient rule. We have rewritten the limit of a fraction as a fraction of two separate limits. We now have an independent problem on the top and an independent problem on the bottom. We already know from our safety check that the denominator evaluates to 2. For the numerator, we evaluate the top limit by substituting 3 into the expression 2x plus 4. This breaks the complex fraction down into simple arithmetic, showing exactly why the algebra of limits is so useful. To finish the problem, we just perform the multiplication in the numerator. 2 times 3 is 6. Adding 6 and 4 gives us 10 in the numerator. We are left with the simple fraction 10 divided by 2. We perform the final division to get our answer, which is 5. This tells us that as the input value x slides along the axis towards the number 3, the output value of this entire fractional function smoothly approaches a height of 5. The algebra of limits made this complex fraction incredibly easy to handle. You might wonder why we spend so much time learning these rules when we could just plug numbers into a calculator. The algebra of limits is the foundational bedrock that makes all of advanced calculus possible. Without these rules, every single time we wanted to find a derivative or an integral, we would have to write a massive multi-page epsilon delta proof from scratch. In the real world, engineers use these principles constantly when designing complex systems. For example, an aerospace engineer calculating heat stress on a rocket can calculate the limit of heat from air friction, exhaust, and solar radiation independently and safely add them together. To wrap up our lesson, let us review the key takeaways. The algebra of limits is a powerful toolkit that proves the limit of a combined function is equal to the combination of its individual limits. Whether you are adding, subtracting, multiplying, or dividing, you can break large, intimidating expressions into small, manageable pieces. As long as the individual limits exist and you remember to never divide by 0, these rules allow you to turn complex calculus expressions into basic arithmetic. You have now mastered the foundation needed for advanced calculus.